Welcome back. This is Fundamentals of Micro and Nanofabrication. My name is Sushoban Avasthi. I am from IIT Bangalore, and today we are going to talk about the first of the additive steps in microfabrication, which is diffusion. So, I think you must remember this slide from before. If you take silicon, you can actually dope it. That is what makes it a very good semiconductor. You can, for example, add some group 5 element which will create an n-type doping, and you can add a group 3 element which will create p-type doping, and this allows us to tune the conductivity of silicon, and which is useful in applications. Now, the question however is, how do you create doping inside a material once you have made the crystal? So, you can always add some doping at the start of the crystal, but after the crystal process is done, what can you do to change that doping? So, one of the ways you can do that is through diffusion. And diffusion is actually one of the very important ways in which we make a p-n junction. What is a p-n junction? P-n junction is when you take p-type material and n-type material and put them in close proximity. Actually, let me get my pointer here and put them in close proximity, and that creates a gradient for carriers where the holes in electrons go left and right and form a depletion region. Long story short, you form a p-n junction. And this p-n junction is one of the fundamental devices that you can actually make. So, I will not go into the details of what is p-n junction or why is it useful, just the fact that in order to make a p-n junction you can use diffusion. One more caveat, the diffusion that I am talking about, this is diffusion of carriers. This is not what this lecture is about. In this lecture, we will talk about diffusion of dopants through the material at higher temperature. So, how do you form p-n junction? Very simply speaking, there probably are two ways. One is that you deposit a p-type material on top of the n-type material. So, you take your silicon wafer and you deposit a p-type silicon on top. This is what would happen, say, in a chemical vapor deposition process, and that would be a future module that we will do next week probably. But another way you can think of doing this is, instead of depositing p-type silicon on top, you can just interpenetrate p-type dopant, say boron, into the n-type material, that is silicon. And if the concentration of boron is more than the concentration of the n-type dopant, then you would form a p-type region on top of the wafer, right. So, this material is interprinted. So, you have not added any new material, you have changed the properties of the surface. So, this incorporation of dopants is done via diffusion. It is one of the oldest semiconducting processes we know. In modern terms, we have also started doing with implantation, which we shall also cover later in this module. So, let us first do diffusion. Once again, this is a slide you have seen before when we are talking about defects, but basically any crystalline semiconductor will have certain vacancies and interstitial at any given moment temperature, just because of entropy. On top of those, you can introduce some added impurities, and those impurities can also be either in the substitutional or interstitial positions. Here is an example of how diffusion can occur. So, there can be two mechanisms. So, supposing you take a silicon atom and you introduce an impurity from outside, and that impurity can just shift position from one interstitial position to another interstitial position. When this happens, this is called interstitial diffusion. One of the features of this is it does not need a vacancy. It does not require a silicon vacancy to move. It can move on its own because interstitial positions are present all around in the lattice, and hence this process tends to be faster. In terms of thermodynamics, that basically means that the activation energy of this process is low, typically around 0.5 to 1.5 eV. Often this is done by impurities that are small in size. So, hydrogen does this, a lot of metal impurities do that, oxygen does this in such silicon. Then another mechanism in which the interstitial sits at the substitutional site. If it sits at the substitutional site, then the only way it can actually move if it finds another vacancy close by. Now, there are vacancies that are floating around in this whole material, again because of conformation, because of entropy, there are always vacancies in the system, but that vacancy must be near to this impurity. So, only when these two are close by can this impurity hop in, and that makes this process slower because you are always waiting on an impurity, always waiting on a vacancy. In terms of thermodynamics, that means that this process tends to have higher activation energy, around 3 eV or so, and this is mostly done by impurities that have a larger size. So, they fit in the silicon lattice position, but are unable to move into the interstitial position. Arsenic is a good example, antimony is a good example. Now, if you are talking about diffusion, the primary reason you want to do diffusion is you want to introduce dopants, right. So, you are focusing on materials which create doping. So, you are looking at boron, phosphorus, arsenic, antimony, etc. So, just to give you a sense of just to give you some visualization, here is a slide that actually showed what interstitial diffusion looks like. So, this is the surface that is exposed to the red atoms, which are your impurities, and with time, given enough temperature, these red atoms will just sort of sneak their way in through moving from one interstitial position to another. And the other example is the substitutional diffusion mechanism, where once again here is a surface, you introduce the orange atom, which are your impurities, and those orange atoms will move inside the material just by diffusion, going from higher concentration to lower concentration, but would do so through vacancy. So, a vacancy gets created, the atom moves in, then waits for another vacancy to be created nearby, moves in, etc., etc. Now, in order to model this diffusion process, there is Fick's law. Now, to give you a little, let us discuss a little bit to give you a little more fundamental feel for how the diffusion actually occurs. Supposing you had a box and in which there was just one particle that was randomly moving around. The modeling of this particle inside this medium is not very easy. It is a stochastic process, it can be quantum mechanical process, you need statistical mechanics to actually model this. But as you start increasing the number of particles, you get to a point where while individual particles are doing random walks, but the ensemble of particles is doing certain predictive motion. And if you go to the extreme where the number of particles is so large that it is not possible to talk about individual particles, but only talk about a population, in those cases things start to become much more easy to model. Fick's law is that case. So, Fick's law only works when you have a large ensemble of particles. It only works when the law of large number applies. It does not apply to individual random walks, it applies to the population. And the population would basically simply move from one direction to the other depending upon a concentration gradient. So, the flux or the number of particles moving per centimeter square per second, which depend upon the gradient of the concentration. So, it will move, the material will tend to move from large concentration to smaller concentration. This is exactly how the sense of smell goes from one end of the room to the other end. There are some particles, there are some smell particles that are being created in one corner of the room, and just by diffusion they will go from an area of higher concentration to an area of lower concentration. This is very similar to the diffusion of carriers. The only difference is this diffusion constant d is much more different. There is also a negative sign which simply tells you this is simply a mathematical way of saying that it is going from higher concentration to lower concentration. So, it is negative of the gradient. Then the Fick's second law tries to take it one step further by saying that matter cannot be created or destroyed. So, if the matter cannot be created or destroyed, then the flux of material that is coming from the left hand side and the flux of the material that is leaving must change the concentration in that small box. So, if you take the 1D case, you have Jx, which is the flux coming in from the left hand side, you have Jx plus Dx, which is the flux leaving, and then the change of concentration in the small element dx is nothing but the difference of these two fluxes. And if you just simplify it further, you basically see that the concentration change with time is equal to the concentration change, the double derivative of the concentration change in the double gradient of the concentration change with a negative sign and a diffusion constant d. If the d is independent of concentration, then you can take it out, and this gives you the simplified form of Fick's second law, which is the typical case used in most mathematics on fabrication. So, the concentration gradient with respect to time is equal to negative d, which is the diffusion coefficient of the double derivative of concentration gradient with respect to distance. Now, this is a second order differential equation. So, in order to solve it, you need one initial condition, which is a time condition, and you need two boundary condition, which is in space. Right? So, let us solve it for two generic cases that sort of come often in diffusion, in dopant diffusion. So, the first case is what is called the infinite dopant case. So, supposing you take your silicon and then you add dopant to one side. So, there is a high concentration of dopants here and there is no dopant here. So, of course, the diffusion will mandate that the dopants will move in from left to right. But let us assume that the dopants are in such plethora that they are nearly infinite. So, the concentration of dopant will not change as the dopants diffuse inside the silicon. So, there are so many dopants that a few of them diffusing into silicon does not matter, right. So, if you take that extreme case, then the initial boundary condition is very simple. Inside silicon there was no dopant. So, Cx was at t equal to 0 was 0 everywhere. The boundary condition is also relatively simple. At starting point you have some concentration, but that concentration will not change with time. So, at x equal to 0 the concentration will remain fixed irrespective of time. And very far away on this extreme, say supposing the silicon is infinitely long, at very far away at the extreme end, no matter how much you diffuse, you will never have any concentration. So, there will always be a gradient and the concentration far away into the bulk of silicon is 0. With these conditions, if you solve that double differential equation, you will actually get this, which is an error function profile. I have plotted the error function profile here, the normalized profile as a function of depth. Once again, it looks like what you think it should. At the surface where the dopants is starting to diffuse, you have a very high concentration. As you go deeper into the bulk, the concentration falls and it asymptotically goes to 0. If you now look at the number of atoms that have diffused in, right, that is given, that is called the dosage, and that is simply the area under the curve of this concentration curve, right. So, you are simply integrating it under, and if you integrate it under, you basically know how much with respect to time, how much carriers are diffusing inside the material. So, this is simple math. You can take that error function profile and integrate it and you get this. Now, if you look at this formula, there are two things that are apparent. Number one, the amount of carriers that have gone inside is proportional to this value Cs, which is the fixed concentration that you are maintaining at the surface. So, if you want more atoms to diffuse in, then you should increase the concentration of dopants at the surface. I mean, that seems obvious, right? If you have more number of dopants, they will diffuse in more. The second thing that you can actually change is D, which is the diffusion coefficient. So, if you want more atoms to diffuse in, you must find a dopant that diffuses faster, that has a larger D. Finally, there is time. So, if you want more atoms to diffuse in, if you want a thicker p-n junction, if you want a thicker doped region, then you should just give it more time. But both D and time are under root dependent, which is that they are sublinear. In order to increase the number of dopants that have gone in by 10, you need to increase the time 100x. So, at some point it becomes practically impossible. That is why diffusion is only useful to create a certain thickness of doped region. It cannot create arbitrarily thick dopant regions. Finally, if you look at the concentration as a function of time, you would notice that at the surface, the starting surface, the concentration is fixed, which was our fundamental assumption that there is infinite dopant there, but with time it is becoming deeper and deeper. So, if you look at the curve, it is becoming, it maintains its shape, it just keeps becoming broader and broader. And to a good degree, this depth of penetration is simply under root dt. Is simply under root dt, or some function of under root dt, some multiple of under root dt. Now, if the amount of concentration at the surface, in order to increase the doping, if you want to increase the concentration at the surface, the next question is, what is the maximum concentration that I can actually maintain at the surface? So, the maximum concentration you can actually get is the solid solubility. So, it does not matter how much material you put on the top, ultimately silicon as a solid can only accommodate a certain amount of impurity inside. So, the best you can do is solid solubility, and the solid solubility often is a function of temperature. It increases with temperature and at some point it starts decreasing with temperature. It has this U-shaped curve. In general, for the various dopants that are of interest, which is antimony, boron, phosphorus and arsenic, Typically, the solid solubility limit ranges from around 0.1% to around 10%. Things like arsenic, which are better lattice matched to silicon, that concentration tends to be higher, around 10%. Things like antimony, which are not lattice matched to silicon, so the antimony does not like getting inside the silicon lattice, that solid solubility tends to be lower. If you look at this shape, this should be familiar to those of you who are familiar with phase diagrams. Solid solubility is something you can actually extract from the phase diagram. Now, phase diagrams per se are not part of this course, they are sort of optional reading, but for those of you who did the optional reading, the next slide is important. So, if you take the phase diagram, say between arsenic and silicon, and if you look at the corner where you look at the pure silicon part of the phase diagram. So, supposing you look at this line, so this is the solidest line, right? But if you zoom in, what you actually see is exactly the solid solubility curve, because this is the amount of arsenic that can actually dissolve inside the silicon while not phase segregating. So, this is the maximum amount of homogeneous dissolution of arsenic inside silicon. Solid solubility curve is nothing but this line in the phase diagram. All right. Finally, it is also important to remember that solid solubility does not mean it is electrically active. When you are trying to do doping, when you are trying to create a p-n junction, you want a certain amount of dopants, but the assumption there is that those dopants would each give you an electron, or if it is n type or if it is p type, that will give you a hole, but that does not always happen. If you look at this, for example, arsenic, even though arsenic has around 10 to the power 21 or above solubility in silicon, the arsenic that is electrically active is an order of magnitude or at least half of it lower. So, it is only 5 into 10 to the power 20 or something. If you look at phosphorus, the difference is even larger. For antimony, on the other hand, the difference is minimal. So, what that means, if you were to create a gradient profile inside silicon, so here is again a concentration profile. So, it goes up, it goes down, but all of these excess dopants are not electrically active. So, the effective doping is significantly lower. This is the dotted line. So, you have to be a little careful. At the very high end, you are limited by solid solubility, but even when you are limited by solid solubility, the actual dopant concentration is even lower, right? The actual achievable dopant concentration is even lower. So, some of these excess carriers can just form clusters which are electrically inactive. Another interesting case where you do want to solve the Fick's equation is the finite dopant source. So, in this case, the assumption is once again that you have the dopant at the surface of the silicon. This is a 1D system where silicon does not have any impurity to start with. However, this time the dopant is not infinite but finite. So, you have put in certain number of atoms and those are finite, you do not have excess of them. Now, the boundary condition is slightly different. The initial condition remains the same, the boundary condition remains slightly different, which is that now the amount of dopants that have diffused in or are available to diffuse in is constant. So, the area under the curve must be, which is the dose, must remain constant. So, which is S, this integral remains constant, that is the boundary condition. So, with that, if you solve the Fick's equation, you get this Gaussian profile. So, this is a typical Gaussian, half of a Gaussian profile. The shape is still monotonically decreasing. So, at the surface, you have very high concentration, limited by solid solubility or other aspects, we will just look at it in a minute. And as you go deeper into the material, the concentration falls and it asymptotically goes to 0. If you now look at the number of dopants that have gone in, which is your dose, unlike before the infinite source case, here that is fixed, right. So, as you diffuse for longer and longer, the profile remains Gaussian. However, the area under the curve remains conserved. If the area under the curve remains conserved and the material is moving in, then the peak must fall, right. So, you start at some point 0, if you started with very high concentration, with time that concentration will fall and the film will become broad such that the area under the curve remains constant. If you were to compare this infinite and finite diffusion profiles, they look something like this. The common themes are, in all cases, the effective depth of diffusion is some multiple of under root dt, right. So, it is sublinear. In order to get twice a thickness of dopant region, you need to give 4 times the time or 4 times higher diffusion coefficient. In the infinite source, the surface concentration remains fixed, does not change. In the finite source, it changes, but the area under the curve remains the same. In one case, we have an error function profile, in the one case, we have Gaussian profile. Now, let us talk about diffusivity and its dependence on temperature. In general, diffusivity is an exponential function of temperature, and that is because in order for an atom to or an impurity to diffuse, it must go from an initial position and go to a final position. But in order to go do that transition, it must overcome a hill. So, it must overcome a barrier, and that barrier is typically given by EA. And depending upon whether it is substitutional or interstitial, this value of EA can be different, but for all impurities there is a certain EA that they have to face, and depending upon that EA is large or small, they will have different temperature dependencies. One easy way to increase the diffusion coefficient, however, is to increase the temperature, right, because it is a very strong function of temperature. So, if time is a weak function of temperature, because in order to increase the depth of diffusion, the time was under root T. So, to make the depth twice, you had to increase the time 4 times. However, D and it depends on temperature exponential. So, it is very easy to increase D by increasing temperature a little bit, and the D becomes an order of magnitude higher. So, the effect of dopant thickness on temperature is much more strong than the effect of thickness on time. If you want a deeper junction, it is much easier to increase the temperature, it is much harder to increase time. Okay. So, that is the intuition is useful for you to keep in microfabrication. Now, what is that exact value of diffusivity really depends upon the impurity you are talking about. So, let us take 2 cases. So, let us take first those impurities that are interstitial, such as metals. So, gold, copper, iron, they all tend to be impurities that are interstitial. It also happens that these are not dopants. See, they are interstitials, they can't be dopants, right. So, these are also those impurities that we in general want to avoid inside a semiconductor, right. So, these are problem cases, these are things we do not want to diffuse. However, because they are interstitial, their activation energies are lower and the values of diffusivity coefficients are higher. It is easier for these impurities to move. Typical value is around 10 power minus 6 centimeter square per second. Of course, it varies with elements. The other type of impurities which we want to move are those that are substitutional. So, these are the dopants, these are the boron, arsenic, phosphorus. This is what we want to move, because the whole point of doing diffusion is to create a dopant, it is to create a dopant region. But because they are substitutional, they have higher activation energies and they have smaller diffusion values. So, their diffusivity is around 10 power minus 12. So, you see this is 6 orders of magnitude different. So, the things that we want to diffuse, diffuse slower, things that we do not want to diffuse, diffuse faster, and that is a problem. So, if in your diffusion you have any impurity, you have any metallic impurity, you have any you have metal impurity coming because the furnace is unclean, you have metal impurity coming because you have kept the wafer on top of a metal piece during annealing, all of those metal impurities will go much deeper inside your silicon substrate than your dopant atoms will, and that is why purity is so essential. During cleaning, we again stressed on the fact that we want to reduce metal contamination as much as possible. This is the reason why, because any metal contamination will move very fast inside your silicon and go very deep, and hence completely contaminate your silicon, and it will go so deep that it is virtually impossible to take it out. So, before any high temperature step, please be very careful in cleaning. Any contamination that happens on the wafer will stay there, go deep inside the wafer, and is virtually impossible to remove. Just to further drive home the point, here is a comparison of diffusivity of gold. Gold is an interesting impurity in silicon because it can do both substitutional as well as interstitial diffusion. So, it is the same element, but it can do both mechanisms, and the two mechanisms have very different diffusivities. So, the diffusivity of the interstitial gold is orders of magnitude 10 power 8 orders of magnitude higher than the diffusion of gold in substitutional mechanism. So, once again, this is why metal contamination is so bad. Any metal on the surface will diffuse more than your dopants will. So, in the same amount of time that your dopants are going 1 micron, your metal contamination can go hundreds of microns and completely contaminate your wafer. What are the various equipment do we actually use, what are the various sources and equipment that we actually use for dopants? So, in general, the equipment looks something like this. So, you have a diffusion tube, which is an ultra clean tube with no impurities. Inside, after cleaning, you load your wafers on top of a quartz carrier. That too, that quartz has to be ultra pure. This can't be, and nothing here can be metal. Then you flow some gas, and that gas hopefully has the dopant source, right? So, if the gas has the dopant source, what is the source of boron? A common one is diborane. You can have arsine, phosphine. Unfortunately, these hydrides tend to be very poisonous and dangerous, so often not used in practical commercial applications. Sometimes, if you don't have vapors, you can have solid precursors. For example, you can use boron nitride for boron. You can use arsenic oxide or phosphorus oxide. You can also use liquids. You can use boron halides, arsenic halides, or POCl3. All of these are liquids that are higher vapor pressure. So, you just bubble through some inert gas, and then the liquid goes, and the liquid forms vapors, and those vapors are then transported on top of your wafer or to your wafer. So, let us look at each of these things in a little more detail. So, this is the oldest, or rather probably the first way in which diffusion was ever done. So, you load your silicon wafer, you keep a little vial or little boat of your material that you want to dope with, say arsenic oxide, and then you heat the whole system, and just by diffusion all this material will go from your boat, get deposited on top of your wafer, and do the diffusion. This is a very old methodology. It does not lead to very uniform diffusion because this wafer sees more dopant than this wafer. So, commonly this is not used anymore. One thing, however, you do need to do is, because if you are dealing with things like arsenic, they can be very toxic. So, you must have a burn box or a scrubber to remove the arsenic before you let the exhaust out into the open. So, that's something you have to be very careful in semiconductor. Any material that is coming out must be treated. You cannot contaminate the environment. A more popular and a more modern method of doing solid state diffusion is using discs or wafers. So, what you do is you take your furnace, and in between two silicon wafers you add a boron nitride wafer, and if you heat the boron nitride wafer in oxygen for a certain time, it will form boron oxide, and that boron oxide can then go and dope silicon. So, there is some sort of proximity doping if you want. So, this allows you much better control and much more repeatability. A lot of liquid sources are also very popular. For example, silicon solar cells often use liquid doping. So, they have a bath of POCl3 in which they flow an inert gas. So, the inert gas is bubbled through this POCl3, and as it goes through this POCl3 vial, it picks up the POCl3 vapors and gets saturated with those, and then those POCl3 vapors go with the nitrogen and get deposited inside the chamber. There POCl3 reacts with oxygen, forming phosphorus oxide, and that phosphorus oxide reacts with silicon to form phosphosilicate glass, and that phosphosilicate glass has the phosphorus that gives you the doping, right. So, this is very commonly used, but once again you are forming things that are dangerous. You are forming chlorine, you are forming phosphorus oxides. In general, you want to have a scrubber and a burn box to capture those before you release it into the atmosphere. Much cleaner but a little more hazardous is to use gas sources, where, for example, if you have diborane and you react with oxygen, you form boron oxide, and everything here is vapor phase. The boron oxide gets deposited on top of your wafer, and you get your doping. Once again, you need a burn box or a scrubber to clean all the things that you do not want to dump outside into the atmosphere. So, here is an overview of the various type of dopings you can do. So, you can do N type, P type. using boron and phosphorus. Then you can also use arsenic and antimony for n-type doping in special cases, but these two tend to be the most common. If you want to understand some of their properties, you have to understand the misfit ratio, which is the difference in the size. So, if silicon is 1, boron and phosphorus are smaller than silicon, so they have a misfit ratio that is less than 1. Arsenic is nearly matched in terms of size with silicon, and antimony is larger. So, what are the sources for boron? Say it is boron oxide, boron nitride. You can have some liquids which are halides, some metal organic liquids. You can use some gases. There are also some spin-on sources. So, here the idea is that there is some chemical that is a little thick, viscous. So, you coat this viscous fluid on top of your wafer and then load the wafer. Okay. With phosphorus, you can have certain solid sources, some oxide sources. You can have liquid sources we already discussed. You can use phosphine. There are also some spin-on derivatives. The USP of boron is it is the most usable of p-type. Like if you look in this list, boron is the only one that I have listed as a p-type. All other p-type sources such as aluminum or gallium have their own problems. We will discuss some of those problems in the next lecture. The other aspect is because boron is one of the smallest atoms, also one of the fastest diffusing ones. So, you have to be a little careful. If you are trying to make shallow junctions, boron will go very quickly. Phosphorus is the most used n-type material. It is also smaller than silicon, so it diffuses faster and gives it a higher rate of diffusion. The great advantage of arsenic is that because it has virtually the same size, it does not cause any stress on the film. Remember when we were discussing defects, we had discussed that whether the substitutional impurities smaller or larger in size can cause compressive or tensile stress. The fact that arsenic causes neither is often useful in semiconductor fabrication because it does not cause stress, which means it does not cause dislocations, which means it does not cause defects. However, because it is completely substitutional, the substitutional process is slow, arsenic is the same size, it is larger than phosphorus and boron, so the diffusion rates are low, which can be an advantage because in the modern fabrication, shallow junctions are preferred and arsenic gives very shallow junctions. Antimony has even lower diffusion, it has very shallow junctions and very ideal diffusion characteristics. We will talk about some diffusion non-idealities in the next lecture. Antimony does not have any of them. So, with that we come to the end of this lecture. In the next lecture we will look at some advanced diffusion processes and some non-idealities. See you then. Thank you.